Excellent. So at causaLens, we build machines that can reason. And that is, I'll talk to you today about a fundamental breakthrough in science and the implications for this new science in the context of trust, explainability, ethics, everything, all of the above. I think it's our fundamental understanding that the current approaches to machine learning, which are essentially just learning some historical patterns, will not get us very far. We are on a track to create quite a dystopian society in which whether your kids go to the right school is decided by an algorithm, whether you're able to go on the property ladder is decided by an algorithm, whether you get a university place is decided by an algorithm. Everything in the future will be decided by an algorithm, more or less. And if we continue on the current trajectory of just putting plasters on correlation-based machine learning models, we will end up in this dystopian society in which autonomous vehicles crash because they don't understand the world. You get turned down for the mortgage for your dream house because the algorithm was unfair. So I think, I think Luke mentioned some really nice frameworks around, how to put plasters on existing machine learning models. But I think we need a fundamentally different approach in order to get to the destination that all of us in this room agree on, which is, we all value the potential of artificial intelligence, but we must do it right for it to be embedded in our society. So this is, in a nutshell, what machine learning today can do. And so, obviously, contrary to what you read in all sorts of media articles, where if you don't know anything about AI, it's portrayed like it's kind of solved, that it's super intelligent, it can do everything, it can play games, and it can drive cars, and it can make decisions. But the reality is that we're kind of at this level of AI. In fact, current AI doesn't really even understand that there are two black kittens in the picture. It just understands that this collection of pixels, most of the time, statistically speaking, results in a kitten. So there's actually a huge way for AI to go to be able to understand things like, if I have a situation where I need to work and I need to feed the dog, what do I do first and what do I do second? That's like a kind of an impossible thing for machines today. They can just look at this, and there's loads of pixels here, and I will just learn some patterns from those pixels. And as long as those pixels match in the future, great, I can identify kittens. But there's so much more to reasoning than what current machines can do. So human brains are just so much more advanced than today's AI. And it feels to me when I go to conferences and speak to people in our field, there is this understanding that we're kind of done with AI. We figured it out. All we need to do now is make sure we put it into production better. But I think we must take a step back and actually change the science fundamentally first, and then do everything else. Because with the current approach, we're just going to be looking at some pixels, or in the case of, I don't know, if you're doing credit approvals, you're just going to be looking at some historical correlations that will drive all the decisions. So we must do better first on the science side of AI in order to achieve all the things we would like to achieve here. So today I'll talk to you a little bit about why AI needs a new direction, what are the implications for the regulatory considerations, implications for regulatory stuff, and I'll introduce the concept of causal AI, which we believe is the future of how AI will be embedded in society. So just a quick motivation of why you would like to consider a completely new way of doing AI. This is a funny example here, which says there's a correlation between sales and shaved heads, which would imply that everybody needs to shave their heads in order to improve sales. And it's just an infographic, but we've seen stuff like this in the real world. We've seen spurious correlations in the models of our banking clients, insurance clients, hedge funds, supply chains. There's a famous paper that showed that the peanut butter production in Bangladesh was perfectly correlated to the S&P 500 for like 18 years or something. And if you use today's approaches to AI, it's a bit of too much of a bigger word, to this curve fitting machine learning, you're going to be learning that sort of stuff all the time. And because we have this complete segregations of data scientists in a dark room in the basement, business somewhere else, we have this infinite loop of, I give you spurious correlations, you look at them, you're like, no way, how can peanut butter production predict the S&P? And this kind of cycle goes on forever until eventually, we get a situation in which we've humanly taken out the spurious correlation. But there is a better way, and we'll talk about that. The US and the EU are starting to care a lot about regulation in AI. And if you read the latest paper from the EU, essentially says we need a new science, and causality is the way to get us there. So I think this is already actually in the working of the EU, and the US is actually getting very close to the same conclusion. So I think fundamentally we all agree that AI could be in a lot more places than it is today, and there is there's essentially a missed opportunity. But we don't want to create this dystopian society that I talked about at the beginning, in which everything is decided on machines that we cannot trust. So for us, all of these things are really important. Explainability, fairness, bias, they're all really important, but it boils down to trust. Essentially, the question is, can we trust this algorithm to make important decisions for us? For us to develop that trust, we must be sure that the algorithm is performing well. If it's doing worse than a coin cost, we might as well throw coins, right? We must, and that's the issue of overfitting. It's a massive issue in today's machine learning, and neural networks are particularly bad at that. We must ensure, to trust an algorithm, we must know it's not biased to a particular gender or race or whatever. Explainability. If we don't have the business and the compliance teams behind us, we cannot put things in production. But we cannot go to the compliance team and be like, hey, I did this sklearn thing, and these features came out, and here they are. Do you like them? Let's put the model in production. It's not going to work. We need to find a common language for the compliance team, for the data science team, for the business, to speak through, and all align on what can be trusted. So I think for us, it's an issue of trust, and right now, it's very hard to find, an executive or even a normal person in using their Alexa at home that trusts the machine. And I think we must bring a new science to the equation in order to change this. I think we need a world in which humans and machines can work together, but not in the today's approach of we put a data scientist in a dark room, they do some stuff, they ship it to the business looks at it as like, oh, this makes no sense, let's bring it back to data science. I think we must find a common language that everybody aligns on. And today I'll introduce that common language. So the common language is a causal diagram. And so causal diagrams are, this is a very simple one, and I'll show you some more real ones in a second, but just want to spend a little second here explaining what causal diagrams are and why they are the future of human-machine interfaces. There was actually a study that came out early on in the pandemic, early on in the kind of the vaccination stage, probably a couple of months in, which basically shows statistically that more being vaccinated increases the chance of going to hospital with COVID. And it was relatively sound statistical analysis. But the problem was that they haven't taken into account a confounder, which was age. And because the current approaches to doing machine learning are all about one-to-one correlation searching, you would never be able to find a confounder in your data. And so had they used causal inference, what they would have realized with exactly the same data, by the way, they didn't have any bad intentions, those scientists. They were just trying to, pick out correlations from data. Had they used causal inference, what they would have learned is that there's a confounder here called age. And that could have been in the data, or it could have been something that a domain expert said, look, we need to consider age. It's important. Whether it was in the data or a domain expert said it, what they would have learned is that age both affected the likelihood of getting vaccinated and also affects the likelihood of going to hospital. And therefore, when you consider the confounder of age, causal inference would have learned that more vaccines means less hospitalizations. And that would have been the right conclusion. So this is just like a super simple causal diagram to illustrate the point. This is how a more real causal diagram would look like that is used by our customers to make better decisions. And what you'll see here, this is just an example of, a marketing example. How do we prevent customers from churning? But what you can see here is a workflow where the data scientists and the compliance teams and the domain experts all look at the same causal diagram. There's no longer a situation in which we have the data scientists in the lab, we have the business consuming some reports from the data science team. We now have everybody on the same page, and we can use algorithms to help us figure out these causal diagrams. This is the process of causal discovery. And we can use domain experts to introduce additional knowledge that may not be in the data, which is super important. A lot of data, we have as humans a lot of knowledge in our skulls, and we must use that in our algorithms. And this is the only way we can bring that knowledge in. But it's also a way for the compliance teams or whoever you would like to make sure that we can, one, develop models really fast, like 10x or 100x sometimes faster, and we can all align on what this model is doing. The cool thing about causal models is that we no longer have to sacrifice performance and explainability. And we no longer have to sacrifice actually anything. We can have both the performance, better than neural network or your favorite traditional ML algos, and we can have full explainability, and we can have trust, and we can have lack of bias. We can have everything in one place. But we just need to use causal diagrams as a way to do it. So here is an example that was alluded to earlier in the case of kind of credit risk, and in this particular case about loan approval algorithms. So if you're concerned about age or gender or anything that you may be thinking, will I go to court for this? Am I making a biased decision based on certain factors? A domain expert or a compliance expert can come in here and say, well, let's introduce these things, and let's actually figure out whether they're confounders. Kind of how age was a confounder for vaccinations and hospitals, we can do exactly the same for credit risk. We can just say, well, let's put age here and rerun this and understand whether we're making decisions based on a confounder. And I guess back to the point, what is an acceptable threshold fairness? Maybe it's 0, and that's actually okay. In this case, it's 5, but why not have it 0? A causal model can actually help you do that as well. So we all know that that fraud is a big deal, and there has been an explosion of fraud since the pandemic. People being more connected to the screens and being at home and being more bored. There was a perfect opportunity for fraudsters to go and try to exploit that, and there's been an explosion. It's always like a cat and mouse thing in the case of fraud, not just in banking, but obviously more general. And so if you have a very static machine learning algorithm, and why would you have a static one? Well, you will have a static one because currently to go from the lab to production takes years. You have to go through all of this compliance checks and credit model risk teams and all of this stuff. It takes years. So if you put something in production, you don't want to touch it, more or less, because you have to do another 3 years of work to get back to there. And of course, this is great for the fraudsters because as soon as they realize how the algorithm works, they change their tactics, and here you go. You just have a great opportunity to defraud people. And so I think on the other hand, though, if you have a live version of this causal diagram, that compliance, credit model risk, data science, business can all be aligned on at any one time, you actually never have to think about what do we have in production. You have in production what everybody is seeing at any one time. And these relationships here are not linear necessarily. They can be, but they're not necessarily linear. And in most cases, the real world is not linear. You can see here the relationship between age and scam is very nonlinear. Early in your life, while you're figuring stuff out, you're more likely to be defrauded. Then you learn stuff, and you're like, OK, I've got this. And then you get a bit older and perhaps lose the edge a little bit, and the curve goes again. And that relationship is one of these arrows here, where there's age, age and scam. So this particular red line here, which indicates a negative causal relationship, is described by this particular function. But everybody can see this, and everybody can say, well, that makes a lot of sense. And if the world changes, they can see it again. And until the point they're not happy with how this works, this model is adapting, living, and making it really hard for the fraudsters to catch up on. But you can only do this if you have this causal diagram that everybody is looking at one time, and it's live moving. And we call this causal ops in our system. So we have a module that will do this and will align everybody to make sure we have the best performing model in production that continuously evolve, but everybody trusts them at any one time. And I think what we forget a lot of the times when we build traditional machine learning models is that they're basically just a function of historical data. But historical data does not have all the answers or all the scenarios that could potentially happen. The historical data is just kind of a one input to a model, but it's not enough. We believe that you must have the ability to understand, to decouple yourself from historical data. So if and I recommend you guys read the book of Why from Judea Pearl. I think as an introduction to causality, but essentially without decoupling yourself from historical data, you have no chance of understanding what happens if an input comes that is completely different from the distribution of your historical data. So if you wanted to understand, for example, what would happen if, as a business, we change the timing of a cyber awareness campaign. Say we did it every month. What happens if we do it every 2 weeks? Would we actually have less fraud? You can't do that today with the current approaches. You can pretend to do it, but we can talk about this more scientifically if you like later. You're violating the covariance matrix because you're changing one thing, assuming everything else remains the same. But if you have a causal model, you're decoupled from historical data. You can start doing these things, these scenarios that do not exist in historical data, and you can start helping the business make the right decisions. So this is just another example of a domain expert coming in and actually describing a function into a particular model. But I think that the idea is the same, that unless we have everybody speaking the same language, that language being the causal diagram, we're not going to move forward with, with trust in AI and therefore the wider adoption. So we think that this approach of causal diagrams and getting everybody on the same page, from our experience, has led to 10x faster deployment in production. And I think we should all aspire to cut the time that it takes to get models in production. Currently, some of the industry average is a little bit scary. They're in the years, and they end up with a suboptimal model that has to be retrained, and another couple of years after that. So I think if we're serious about benefiting from this, I'm done. Benefiting from artificial intelligence, we must do it differently.